And so essentially what I said is that if we know the distance redshift relation z as a function of d, then this gives lambda as function of t. Okay. So let me write down the abstract relation first, and then I'll try to do the expansion in powers of t minus t naught. So d we know is given by integral t to t naught dt prime over lambda t prime. Okay. So here t naught is today's time always. Okay. T is the time at which we are observing the star. Right, whatever you are observing, that time we are calling t. Okay. And so the distance, okay, will be given by this formula. Okay. So earlier t is the larger is the distance, right? Because larger distance requires more time. Yes. Yes, exactly. Is the time when the star emitted the light. Okay, so let me write this. This is what I was calling T1 last time. Okay. On the other hand, Z we define as 1 over lambda of t minus 1. Yeah, t naught is today, right? Imagine that you are receiving it today. T naught is today's time. So that's the convention I'll always use. T naught will be used for today's time. So this was essentially the definition of Z. Right? Today lambda is 1, right? So Z is 0. And we define Z as this. That gives a redshift. So then this relation can be written in a compact form as by saying that 1 over lambda of t minus 1 is equal to f of integral t to t naught This is the abstract form of the relation. All I have done is that I have substituted in this expression. Right? The left hand side I have written it as 1 over lambda of t minus 1. Right? On the right hand side, inside the argument of the function, d I have replaced by this function over here. And then the claim is that if we know f, we can reconstruct lambda. Right? Because after all, lambda is one function, right? F is another function. Right? So if you know one function worth of information, we can reconstruct another function that satisfies an equation like this. Is this point clear? Okay, so this is an abstract statement. Now let me explain, okay, at least if we want to do a power series expansion, how we do this, right? How we find these various coefficients. So suppose lambda of t is given by 1 plus h naught times t minus t naught minus half q naught h naught squared t minus t naught squared plus etc. Okay, where h naught q naught are unknown. And suppose further that f of d, right, this is distance versus redshift. So when the distance is 0, f of the z is 0. Right? That's the way we have defined redshift. So f of d has the structure ad plus bd square and so on. So these are known. This is what to measure. Okay, now when I say this is what to measure, it's still not a direct measurement. You have to make some inference, because what you really measure is the red shift, okay, as a function of the apparent luminosity, right? How luminous the thing is looking, and from that you have to reconstruct what the distance is. Okay, and the idea is that if you have a standard object, right, whose intrinsic luminosity is fixed, then larger the distance, the smaller will be the apparent luminosity, and that's what we use to reconstruct what D is. Okay, so then this, let's now try to expand both sides of this equation. Okay. On the left hand side, we have 1 over lambda, so you can do it with the expansion. So you get 1 minus h naught T minus T naught plus h naught squared T minus T naught squared plus T naught h naught. We just stop at h t minus T naught square. Okay, but you can keep going if you want. Is that clear? So that expansion just is 1 over lambda minus 1. Okay, minus 1. So this 1 will not be there. Is clear? Right? I just took 1 over lambda. Right? Lambda expression I have postulated here, right? With unknown coefficients. I took 1 over lambda, subtracted 1 from that. On the right hand side, we have B. Sorry, we have F. Okay, so let's try to evaluate this first. Sorry, second term should be 1 over 1 plus x. I am expanding, right? So 1 minus x plus x squared, right? So if you think of it as x, square will be outside the bracket. Oh, yeah, okay, yeah. Yeah, of course, otherwise it's not even dimensionally correct, right? You cannot subtract square of time from time. Yeah, t minus t naught square. Is that okay now? Right? 1 over 1 plus x is what I'm expanding. So here I have f of integral e to t naught dt prime, and again 1 over lambda dt prime times 1 minus h naught t prime minus t naught plus h naught square. Okay, this part we will not really need. Let me write it anyway. Okay, so this I can write as t naught minus t minus half h naught times this is t prime minus t naught, so it's negative, so I think this should be plus. This is t naught minus t is clear, right? This is f of this. This integral is t naught minus t with 1, right? Second integral had a minus sign, but this gives you half of t prime minus t naught squared. Okay? At the upper limit, it's 0. Yeah, at the lower limit, it's t minus t naught. Right? So that's why the minus become plus. Okay, so this thing is sitting inside the argument of f. Okay? And now I use the fact that f has this form. Okay? So this is now given by a times t naught minus t plus a times half h naught t naught minus t squared plus b t naught minus t squared plus order t naught minus t cube. Is it clear what I have done? So a times d, right? So this is the argument, right? So a times whatever is in the argument I have to put, right? And there I stop at t naught minus t square. Then b times d square, right? But when you take d square, you can ignore this because this term will give t minus t naught minus t cube, right? So just I take the t naught minus t square and stop here. Rest of the terms are order t naught minus t cube. And now we can compare this, right? So you see that this tells us that h naught is a. We just compare the powers of t naught minus t because this both sides are this equality is valid for all t. Right? So you can just compare the powers of t naught minus 2. H naught is a. And then the second one tells us that h naught square is half a h naught plus b. Sorry, something is wrong. Sorry, h naught square. I forgot the other term. And so on. You can compare t minus t cube and so on to get the other coefficients. Is it clear what I'm doing? I'm just comparing this with this, right? The first is just order t naught minus t term. The second one is t minus t naught square term on both sides. Okay. So we see that this determines h naught, right? Because a is known. Right? Once a is known, okay, here the only unknown is q naught, right? A and b are known. H naught we determined in the previous at this step, right? So this determines q naught. Right? And this goes on, right? If you want to do a series expansion, then you can calculate all of these terms from the f of t. Okay, to calculate the next order term in this expansion, in the lambda expansion, we need the next order term in this. Right? You need the order d cube term to calculate the t minus t naught cube term in the lambda expansion and so on. Right? So this is when you try to do the small t naught minus t expansion, but suppose you want to calculate the function, if you want a functional form, right, from this analysis, then you have to basically try to solve this numerically. Okay, you have to try to keep adjusting f so that, and given that f is known, you have to keep adjusting this functional form of lambda of t so that you solve this equation. Is this point clear? Okay. So the main upshot of this is that if we know the distance redshift relation, right, you look at far away objects, calculate the redshift and also estimate the distance from this apparent luminosity. Okay, you determine that function. Using that, you can find how lambda is changing as a function of time. Now, I should also say that in this kind of measurement, the distance is the most tricky part, right? Because redshift you can figure out. Okay, how much has the spectrum shifted? But distance, I mean, it really requires knowing the apparent, making sure that the object that you're looking at, right, has the same intrinsic luminosity, right, which is called the standard candle, right, whose luminosity is fixed, and then you are doing your measurement correctly to estimate the distance. Okay, and so in fact, the measurement of h naught, for example, right, the first measurement of h naught that was measured, okay, that was 10 times the current value. Right? So the value of h naught has actually changed by a factor of 10. Okay, because of all these uncertainties. So it's not that you get it at one go, right? You have to keep improving your analysis, and eventually, right now, we have some idea of what h naught is. Any question? how do you measure D? Yeah, so the point is that if you have a standard candle whose apparent intrinsic luminosity you know, right? Then imagine that object emitted some power. Okay, so those photons, right, which are emitted, right, today, when we are saying that today we are at a distance D, right? This is today's distance, right? The actual emission took place long ago. Okay, so that radiation has reached us today, right? But it has also reached everywhere within the distance D from this co-moving object, right? So the actual flux that was emitted has been gotten divided by the area of this sphere, right? And let's assume that the spatial slice is flat, right? Don't worry about the K. Then this area of the sphere is just 4 pi d square, right? So you say that the apparent magnitude, apparent luminosity is 1 over 4 pi d square times total power emitted, right? So if you already know the total power emitted because it's one of the standard objects, right, like type 1 supernova, and you know this is something you can measure, right? So you can estimate D, right? So that's the way you typically estimate D. But there is also another factor here that you have to take into account, because the photons that are emitted with frequency nu, right, are reaching us today not with frequency nu, right? But there is a redshift factor, right? It gets scaled by lambda. Okay? And we know that the energy of a photon, right, is proportional to the frequency. So if the frequency gets reduced, right, then the energy of each photon gets reduced by that factor, right? So the apparent luminosity that we will see, right, besides this, will also have the lambda factor, right? And that's what goes in, right? So so what is this tells us? This it doesn't give us distance as a function of redshift, but a combination of distance and lambda as a function of redshift, right? Because actual luminosity, right, the apparent luminosity will be this multiplied by lambda of t. The lambda of t is the factor by which the frequency of the photon is reduced, right? So what to calculate is this object, right? This combination is what to measure. But that is good enough, because instead of saying if z as a function of d, you'll have another factor of lambda, and then you have to do the expansion and figure out what you get, right? Or lambda, for example, is directly measured, because when you look at a distant object, right, what are you measuring? You are measuring its apparent luminosity, but also its redshift, right? So given that lambda is also measured, right, you use that redshift, so you divide by that measured lambda. Okay. Exactly, that's right. So that's how you compare. So lambda is measured by looking at the frequency shift, but there's an independent object which is the luminosity, right? How much power you are receiving, right? So using those two informations, you can figure out what D of that object is. Okay? That's the way this measurement goes. Okay, and right now the standard for large distances, the standard objects that one uses are the supernova, like type 1 supernova. Those we believe, I mean, I want to understand the theory reasonably well, so that we know what the actual power emitted is.
If the object is far away, is it possible to separate the noise from the light that is coming from very far away? Because there could be other sources as well in the way.
Yeah, of course. I mean, you have to, I mean, any experiment, right? You have to make sure that the noise is factored in. Okay? So that's why there are a lot of uncertainties. You have to make sure that the noise is removed and the various other effects are removed, right? And only then you can make this measurement.
Okay, thanks.
Sorry, you had a question?
So, how do we know exactly the frequency that the observation that we make from the light that is already shifted, right?
Yeah, but that's intrinsic. I mean, that's because the spectrum. I mean, this is what we discussed. If you have many lines, right, sodium and calcium line, right, by looking at the ratio, right, ratio is not going to change, right? So using that, right, the whole spectral line, you can figure out which line is sodium, which line is calcium. right, which have their intrinsic frequencies, right, and that's how to compare with what you measure. Right, so a single line will not work because you don't know what that line corresponds to. Because so this is assuming that whatever was emitted here, right, came here, right? So this depletion, that 1/4 pi d square, you can think of as a depletion of the number of photons, right? If the photons are not interacting on the way, then the number of photons, if the total number of photons emitted was something, right, it will be depleted by this 1/4 pi d square, because that is the number of photons per unit area that we are receiving, right? But each photon, right, started with some energy, h nu, right? Today, when you are observing, right, that energy has gotten scaled, right? Because we saw that nu observed is nu emitted times lambda t, right? So that's what the scaling is, right? So because of this, there is also a depletion in the energy of the photon. Okay, so now we are going to start the part that really requires GR, okay? And that is what happens when you have sources, right? Because we have given the form of a matrix, right? But all matrices are supposed to satisfy Einstein's equations, right? We have not so far put in anywhere that we have that this matrix solves Einstein's equations. Okay? So you have to now understand what kind of sources are present that is responsible for a metric of this kind. Right? That could be responsible for a metric of this kind. So we'll determine the structure of the sources, not the exact form yet, by symmetries. So we want to solve R mu nu minus half R mu nu equal to 8 pi Gt mu nu. And you want to know what kind of T mu nu could possibly give rise to a metric of the kind that we wrote down. Now, there are two ways of doing it. One is that you already know the metric, so put it on the left hand side, right, and see what structure this left hand side has, right? That will tell us what structure T mu nu should have. Yes. That's inside T mu nu. I'm including the cosmological term. If it's there, I'll put it inside T mu nu. Right? So so I'm allowing T mu nu to have cosmological term as of now. Okay, so what I was saying is that since you already know the metric, we can just calculate the left hand side, right? See what structure it has, and then infer what the structure of the right hand side is, right? But that will be somewhat of a cheating, because we want to have an independent understanding of what the right hand side is, and then see that this lambda actually solves that Einstein's equations, right? So we'll determine the right hand side just from symmetry first, okay, the general structure of the right hand side. So now what do you mean by you will determine it from symmetries? Okay, the idea is the following. So under a general coordinate transformation, T mu nu transforms as a tensor, so you know how T mu nu should transform, and so we can write T mu nu of x as T prime rho sigma of x prime. So this is the standard general coordinate transformation laws of any tensor. But now suppose that the general coordinate transformation that we are using is one of the isometries that this metric has. So if the transformation is an isometry, . So what is special about isometry? Okay, what is special about isometry is that under isometry, the functional form of the metric doesn't change, right? And we demand the same thing for also functional form of all tensors that are present in the background, right? Because if the metric doesn't change its functional form, then the T mu nu better also not change its functional form, right? Otherwise, there will be contradiction between the two sides of the equation. So under an isometry, we expect that T prime rho sigma of x prime should be T rho sigma of x prime. Okay, T prime should have the same functional form as the original tensor, original T mu nu. Yes, that if you don't demand this, right, then this equation will be inconsistent, right? Because the left hand side has an isometry, if the right hand side doesn't have the isometry, right? Then you're equating two things, right? One of which has isometry, other one doesn't have isometry, right? So this equation will be inconsistent. So, and so this is in fact part of the homogeneity and isotropy, right? When he demanded homogeneity and isotropy, right? Everything should be homogeneous and isotropic, averaged over large scale, right? Metric as well as the energy momentum tensor, right? And anything else that might be there in the background. Is this clear? So now let's look at the form of the isometry. We have T equal to T prime and Xi equal to, let me write T prime equal to T because you're going to differentiate. Let's say X prime I equal to Fi of X, which you can also invert by saying Xi equal to phi I of X prime. This is the inverse function of F. Okay, this is the structure of the isometry. The main point is that T prime remained the same as T, and these transformations did not invert T. Okay, that's what we had learned in the analysis that we had done earlier. Now you can substitute, and I'll write down the result. This is an easy exercise to check that when you use this, right, just demand that T prime is the same as T. Okay. The TT component tells us that T00 of T x is equal to T00 of Tx prime. Okay, basically these just give you 1, because T is equal to T prime, and there is no dependence of T on any of the x's. The second set of equations is T0i of Tx is given by del x prime k del xi 0 k 0 x prime. And the third is the Tij dx del x prime k Okay, these just follow directly from this form of the transformations. The first equation is easy to interpret, right? T00 doesn't depend on x. Right? Energy density should be uniform over the spatial slice. At a given time, T, energy density should be uniform. Right? To which also intuitively should be clear. Right? If the space is homogeneous, it better be that the energy density doesn't depend on where in space you are in on a given time slice. So one tells us that T00 Tx is equal to just a function of rho. This is energy density. The second equation, right, what is it telling us? Sorry, this is, why did I write 0, t, right? The second equation tells us that if we fix time, take a given time slice, then this is the way a vector field in 3-dimensional will transform, right? Except that there would have been a t prime here. Imagine that there is a vector field in 3 dimensions. Forget about time, right? Time is, we are working at a fixed time slice, right? How does the vector field transform, right? In 3 dimensions, under a general 3-dimensional coordinate transformation, it transforms as this times, this would have been a t prime 0k of t x prime, right? And so this is saying that t prime 0k is the same as t0, right? That's the extra condition you are putting, right? Because it's an isometry. So what this is telling us that the t0k is a vector field in 3 dimensions, which is invariant under the isometry, which doesn't change its form under isometry. Right? The 3-dimensional isometry doesn't change the form of the vector. Fortunately, okay, on these maximally symmetric spaces, right, we know all possible vector fields of this kind, and there are none. Right? The result is that on a maximally symmetric space, right, you don't have any vector field which preserves its form under an isometry. It's not hard to understand geometrically, right? I mean, you cannot visualize 3 dimensions, but let's take the surface of a 2-dimensional sphere. That's a maximally symmetric 2-dimensional space, right? If vector field means given a point, you should assign a vector, right? But imagine that you take rotation about that point, right? A rotation which keeps that point fixed. So that vector will transform to something else, right? It will not preserve its form. Is that clear? Right? On the surface of a sphere, if you try to draw a vector, right, and if you demand that it's invariant under all isometries, right, take the isometry that rotates about the point, about that point, okay, and that will change the direction of the vector field, right? So it cannot be, so it's not invariant, and hence the vector field must be 0. Right? 0 is always invariant. So the second equation tells us that T0k is 0. Yes.
We have a vector field. So even if we rotate, let's say we rotate, so it will change, but because we have isometry, so we can say like because of homogeneity and isotropy, this vector has the same form as the previous one.
No, see, it doesn't have the same form, right? Because as a function, right, think of a given space, right? If you are assigning a particular direction to the vector field, right, isometry takes it to another function, right? But what we need is that that function is the same as the original function, right? That is not true in this case, right? In the original function, imagine that suppose you are at the North Pole, right? And suppose the vector field that I have chosen is in the XZ plane, right? The y component is 0. You're thinking of this as the remaining space. Now, if you rotate in the XY plane, right, North Pole remains fixed. That vector gets rotated into somewhere in the XY direction, right? But it doesn't have the same functional form, right? Earlier, the vector field only had component along in the XY plane and no XZ plane, no component in the XY plane. The new vector field has now component both in the XZ plane and XY plane. Right? So the functional form gets changed, right? And what this is demanding is that the functional form should not get changed, right? If T0i had only component in the XZ plane, then on the right hand side also you should have only component along XZ plane, right? And then this equation fails to hold. Is this point clear? Right. So it is true that if you have a vector field, then under the isometry it will go to another vector field which looks symmetric, right? But that's not what you are demanding is more, that it should preserve the actual functional form. Yes.
That transformation.
Well, I'm demanding that this is an isometry. Otherwise, T prime will not be equal to T. Right? So we cannot demand that under arbitrary general coordinate transformation, T prime and T are the same, right? Functional form. But under isometry, the new energy momentum tensor should have the same functional form as the old energy momentum tensor, right? So I'm saying that only when these are isometries, right? Like in on the 3-dimensional sphere, right? There are 6 isometries, right? If you take these to be any of those 6 independent isometries, these conditions should hold. Right? I have not written down the explicit form of F(i)s, but that we can figure out, right? We identified what those isometries are. Right? The SO4 rotation, for example, for the sphere, right? Or SO3(1) for the hyperbolic space. Right? So you are demanding that these conditions should hold when these are isometries. Right? So similarly, this is just a component form, right? These should hold when they are isometries. Okay? But the statement is that there is no vector field on the sphere which preserves its form under isometries.
Coordinate transformations are isometry will be of this form.
Will be of this form.
We are demanding that T mu should be greater
Under that term, yeah,
follow that.
exactly. I mean, not every transformation of this kind is an isometry, right? But isometries are of this form. And you are just seeing how this equation translates when you take isometries of this form, right? Yes.
What this equation to basically means is to have a vector which says its components in the equal sit in such a way that the same functional form.
Exactly, that's right. Right, and the
Exercise where the functional form of f and phi that doesn't matter.
that doesn't matter, yeah,
For any f phi which includes the isometry.
exactly, yeah.
We intend.
These three are true in that case, right? Making the conclusion, okay, this one, right? It requires that the isometry includes the homogeneity transformations, so that given any x, we can take it to any x prime. Right? Only then we can demand that this is independent of x. Right? So similarly, the vanishing of this requires that you use all isometries, right? Because around defined points, right, there are defined isometries which corresponds to rotation about that point, right? Around the North Pole, it's one transformation. Around the point in the equator, it will be another transformation. But all of these are isometries. And when you demand that the functional form is unchanged under all isometries, right, this condition holds. The third one, okay, can be similarly interpreted. This is a tensor, rank 2 tensor in 2 dimension, in 3 dimension. And this is telling us that the rank 2 tensor under isometry should preserve its form. Is that clear? So do you know of any rank 2 tensor which preserves its form under isometry? Pardon? Delta Ij doesn't quite preserve its form under isometry. Flat space it does, but it is not flat space, right? Yeah, the metric by construction preserves its form, right? And what one can show is that in these maximalist metric spaces, metric is the only tensor which preserves its form. Okay, there is no other tensor which preserves its form under isometric transformation, right? So this means that this Tij must be proportional to the metric, the 3-dimensional metric. So we write Tij times P of T. This is a unique solution, exactly. Pt is some arbitrary function of time, right? Just like rho t, we cannot just demanding isometry, we cannot determine what Pt is, because yeah, if Gij is invariant, then of course any multiple of this is also invariant. This is an arbitrary function. Now I could have written it in different ways. Right? I have chosen to write it this way: Gij Tx, right? I take it to be the full 3-dimensional the metric, the Ij component of the metric, including this A of T whole square factor that multiplies it. You remember the form of the metric? Let me write it. ds square ds square was minus dt square plus a of t square times dr square or 1 minus dr square. Right, this was the form of the metric. So when I wrote gij of t of x, I just take this whole thing. Now I could have just said that gij will only be this part, right? But that just corresponds to absorbing that a of t whole square inside the definition of pt. Right? Pt is an arbitrary function at this stage, right? We have not said anything. So I could have written it in different ways, but I have chosen to write it this way. So this gij that I have written is understood as this whole thing.
How do we say that any other tensor other than GIG cannot be TIGTX there?
Yeah, I have not proven it. This is something that you can show based on maximal symmetric spaces, right? So there is general result in maximal symmetric spaces, just like I said that there is no vector field which is invariant under transformation. You can show that in the maximal symmetric spaces there is only one invariant tensor field, and that is a metric.
Okay, thanks.
So we can do a similar analysis for
R mu nu, we don't have to do anything because once you have the metric, yeah, we can. But once you have the metric, you can calculate R mu nu.
No, like I don't want to calculate it by that.
You can, yeah, it will have exactly that structure, except that these functions will not know. This rho of t will be an arbitrary function, right? Whereas if you already have this,
But I can maybe probably get some like have these components.
yeah, certainly. For example, the fact that Ri0 is 0, right? That follows from isometry. You can calculate it explicitly from here and show it, but you can also check that Rij is 0. Right? Similarly, R00 will be a function of time and not a function of space. Right? That again, okay, it follows from isometry, but you can also calculate it using this metric. Is that clear? Right? So you can use certainly this kind of analysis to find out the general structure of R mu nu. And but the actual functional form, right? R mu nu is determined in terms of the A of t. That you cannot get just from isometry arguments. Okay, but what I'm going to do now is to write down the Einstein's equations. Okay, and it will become clear that R mu nu does indeed have that structure. So Einstein's equations. Okay, I'll not write R mu nu explicitly, but the combination R mu nu minus half R chi mu, right? Because that's what appears on the right hand side of Einstein's equation. Okay, so this again, I'll just write down the results, but this is again straightforward exercise. Okay, you just have to calculate the Riemann tensor and well, straightforward. Yeah, by now it should be straightforward because you have enough symmetries and you should be familiar with how to calculate the Riemann tensor, right? Yeah, it is initially it is not straightforward, but I think by now you should be able to do it. Okay, so TT component is 3 A dot over A square plus A over A square A naught, no. Where is A naught? A dot. A dot, yeah. Therefore, A okay. Dot means time derivative. Okay, at least the final result is simple, right? Even if the actual calculation may be a little complicated. Okay, first of all, the point is if you take k equal to 0, right? Then it's simple, right? Because that part of the metric doesn't depend, nothing depends on x, y, and z, right? Everything only depends on t, right? So you can try to set k equal to 0 and verify this. Okay, ij component. Okay, in fact, ij component gives only one equation. I0 component is automatically satisfied. Both sides are 0. Okay, so nothing comes out I0 component, just for isometry. Ij component, why is there only one equation? Because right hand side you have shown is proportional to Gij, right? But the same symmetry argument, the left hand side is also proportional to Gij. Right? This Rij minus half R Gij, right? It's also tensor, right? So it better be proportional to Gij. And you can do the explicit calculation and you do find that it's proportional to Gij. Okay? So only the coefficients of Gij has to be matched, right? And that's what I'm going to write down. So this gives us yeah, you can conclude that similarly, or you can just calculate it because the metric is given, right? So you can just calculate the 0i component and you can find that it is 0. Is this clear? Okay. So this is all that you have to solve, right? These are the two equations that come out of the Einstein's equations. Okay, ordinary differential equations. Okay. But what we'll do now is to try to manipulate this to make it even simpler. Yes. Well, we'll see what kind of energy momentum tensor we have to use. Right? So far, we have not said anything about what kind of energy momentum tensor we have. Right? But indeed, so you have to analyze that, right? What kind of energy momentum tensor actually enters these equations. Okay, so first, let me call this equation 1 and 2. Now you see that using this, we can eliminate this combination, right, and write in terms of rho. Okay. So I say 2 minus 1/3 of 1, right? To cancel this gives you 2a double dot over a is equal to minus 8 pi g p minus plus rho by 3. Yeah, fine. Okay. Second, you see we have this one has single derivative of a, right? This one has two derivatives. Okay. So you have to try to get rid of these two derivatives somehow. And that's easy because once you have a single derivative, right, you can take a derivative produces two derivative term, and just subtract these two. Okay. So from this we will eliminate a double dot using this trick. Is this clear? So we take d dt of, let's get rid of the a square by 3 times 1. This tells us, this gives us d dt. So this is equal to, let me write right hand side. This is equal to d dt of 8 pi g by 3 a square, right? This is the rewriting of the first equation. Okay? d dt of a square by 3 times 1. So a square by 3 I have to multiply, and on this side I multiply by a square by 3. Sorry, row I forgot. Okay, now the left hand side is d dt of a square by 3. 3 takes care of this. A square multiplication makes it a dot square. So it's a dot square plus k, which is just 2 a dot a double dot. Okay, so this gives us, okay, let me call this 3, and so this gives us 2 a dot a double dot is equal to d dt of 8 pi g over 3 rho a square. Is clear? Right? I'm just manipulating this first equation. First line. Oh, I just took this, right? Multiplied both sides by a square by 3 and derivative, took a derivative. Why is there a square? Here, first line. No. Yeah, see here I'm just multiplying by a square by 3, right? It's up to me what I want to multiply by. First equation, yeah. Yeah, okay, yeah. Okay, this one is the first equation, not one. Okay, so is it okay now? Okay. Okay, so now we have to combine these two. So how do you, so let's call it 4. So let's multiply these by a times a dot. A times a dot, no, a times, yeah, a times a dot will do the job, right? Multiply this by a times a dot, right? So 2 a double dot times a dot is minus 8 pi g over 3 p plus rho by 3 times a dot. This comes directly from 3. Right? So 3 multiplied by a dot. Let's call it 5. And now it has take 4 minus 5. So 4 minus 5 will give us this minus this equal to this minus this equal to 0. So d dt of 8 pi g over 3 rho s square plus 8 pi g over 3 e plus rho by 3 a dot equal to 0. No 3 somewhere? Oh, yeah, thank you. So there is no 3 here. Okay. So this one, okay, assuming that I have done things correctly, okay, the final result is correct. So let me give the final result. So this one we can just manipulate a little bit, okay, to write it as d dt of rho a cube as minus 3 p a square a dot. Okay, this is correct. So if the algebra is done correctly, this is what you should find. Okay, basically you can expand it out, right? You get a d rho dt and some a dot times rho. You can also expand this out and just try to compare, right? A dot will basically cancel out, and there's a factor of a dot here also. There's a factor of a dot, and ultimately you should show that this is equivalent to this. Okay, if this is not equivalent to this, then there is something wrong in arriving at this, right? You just check all the factors correctly. So this one is actually, I can show that you can also think of this as d mu nu equal to 0. This is the energy momentum conservation equation. Because you can see that this essentially involves the right hand side, right? Rho and p, right? On the left hand side also there is rho, right hand side also there is rho, right? So this is something that is coming from the energy momentum tensor, and we know that there is a one condition on the energy momentum tensor that comes out of Einstein's equation, and that is d mu t mu nu equal to 0, right? And this equation you can show is exactly this. Is it clear how to show this? Right? Because the metric is given, t mu nu form is given, right? Just calculate d mu t mu nu and you should find that this gives you this. So at the end we have this equation, okay, and we have this equation. So this equation, let me write. So 1 over 3. So 1/3 times 1. I can write as a dot over a square plus a over a square is equal to 8 pi g over 3 times rho. These are the two independent equations that we have to deal with. I mean, you have done a lot of manipulations, but what one can show, now we go in reverse. So we have got these two equations, right? And one can show that if these two equations are satisfied, right, then these equations are satisfied, right? This equation, of course, is exactly the same as the last equation, right? But by differentiating those equations, you can verify that this equation holds, as long as these two equations are satisfied. But the advantage of doing this manipulation is they have basically gotten rid of the second derivative term. Right? Equations are now only involve one single derivative. Are there questions? So now we see that you have two equations, two differential equations, and how many unknowns? How many functions of t that you don't know at this stage? A we don't know, rho you don't know, p also you don't know, right? So the three functions that you don't know, we have two equations, right? So even if you go give the initial conditions, it's not possible to solve them, right? So we need one more equation somehow. Is that clear? So three functions, we have two differential equations, right? Given initial conditions, you cannot solve for those three functions. Now, this is supplied, this additional equation is supplied by what is called the equation of state. And that requires knowing what kind of source of energy momentum tensor you have. Is this clear? These two equations are independent, yes. Yes, exactly. But we had those two equations. Now we have these two, and what one can show that if we satisfy these two equations, right? First equation, of course, is automatically satisfied, right? Because first equation is one of those, right? Second equation is also automatically satisfied. So you don't have any other equation, right? You have exhausted Einstein's equation by getting these two. Is that clear? So we need a third equation somehow, right? This third equation is what is called the equation of state, and that requires knowing what kind of matter you have. Okay. So let me just give an example, okay, which I think you are familiar with. Suppose you have a cosmological constant. In the Einstein-Hilbert action, if you have a lambda root g term added, right? In terms of Einstein's equation, that basically means that we have r mu nu minus half r g mu nu and plus a constant times c mu nu, right? Let's imagine that you have such a term. So let me maybe first state the problem. So we need one more equation. We have three unknowns, unknown functions, rho p a, and two equations. This means we need one more. Yes. The first of this equation doesn't have a. Yeah, because this is d mu t mu nu equal to 0, right? So d mu t mu nu doesn't have like a gravitational constant. So you basically manipulate the fact that d mu of the left hand side of Einstein's equation equal to 0. That implies that d mu of the right hand side is 0, right? That's why that equation doesn't have the gravitational constant. Okay? This is really the content of the Einstein's equation, right? Other than the energy momentum conservation. Oh, I should have said that this is what is called the Friedmann equation. And this metric that I wrote down, right? The general form of the metric is this FLRW metric, right? You can read out the names of these various people, right? 4 names. Okay? But this equation is called the Friedmann equation. Okay, I'll come to the cosmological constant later. Maybe that. Let me give the first example. So the first example we'll consider is what is called non-relativistic matter. Okay? That's the kind of matter we have in our space in our universe, right? Ordinary stars, galaxies, etc. So they are non-relativistic. Right? In what sense are they non-relativistic? That their speed in this co-moving frame is small compared to c, right? Because you are setting c as the scale of the speed, right? They are almost like not moving. Right? So let's ask, using that, what can you say about the energy momentum tensor, right? Can you get some information about rho and p just from that information, that they are non-relativistic? Okay. So let me remind you the energy form of the energy momentum tensor of a set of particles moving around, right? Which in the cosmological scale, the galaxies are like particles, right? Moving around. So this was given by integral du, so the sum over n. Let me use the proper term d tau n mn one over square root of minus determinant of g. This is a four-dimensional delta function, right? Product of four delta functions. This was the form of the energy momentum tensor of particles that are moving. So if the particles are moving slowly, right, what can you say about the energy momentum tensor? What information can you get from there? So the fact that the particles are moving slowly, right? And slowly means, say, to zero speed. Pardon? Yeah, so only the T00 component will be there, right? Because Tij component, Ti0 of course is already zero by symmetry, right? Tij component will be like the square of the velocity, right? Dxi d tau, dxi d tau, right? And the units that we are using, that's very small. So for non-relativistic matter, we expect that we can set p equal to 0. Because dxi d tau is very small, right? And p is the Tij component, right? So what this is saying is the Tij component will be very small, right? And so in the limit v goes to 0, Tij is 0, right? And that means p is equal to 0, because p is just the coefficient of Gij in the expression for Tij. Is this clear? So if the universe was only filled with non-relativistic matter, then you are done, right? Because we just set p equal to 0, and now you have two equations and two unknowns, right? And once you have give some initial condition, you can solve it. Is this clear? Okay, I have written this equation in terms of A, but when you actually solve it, we'll write in terms of lambda, right? Because A, if you remember, is A naught times lambda, right? That's how we are defined. So this will become lambda dot over lambda, right? And here it will become k over A naught square times lambda square, right? And if A naught is very large, then basically this term you can ignore. So suppose you have a cosmological constant. Okay, so the equation, Einstein's equation can be written as R mu nu minus half R G mu nu is equal to minus 8 pi G times T mu nu. Let's say plus some constant times G mu nu. This was to begin with on the right hand side. Right, I have just taken it to the left hand side and I have extracted a factor of 8 by G and called this some constant. Is that clear? Because experiment tells us that we have cosmological constant. Right? So I'm just telling you that if you have cosmological constant, right, what kind of energy momentum tensor you will get. Right, and what this is saying is that this basically tells us that P lambda, okay, so lambda starts from cosmological term, cosmological constant term. T lambda mu nu will be proportional to, sorry, is C times G mu nu. We just interpret this as a contribution due to energy momentum tensor, just a contribution to energy momentum tensor. Okay? So the cosmological constant, you can regard this as part of the Einstein's equation, okay? But you can also regard this as part of contribution to the energy momentum tensor. Okay, and here that's what I'm trying to do. That's the way we are trying to interpret this, right? Because the way we have set up the Einstein's equation, we didn't have a cosmological constant term on the left hand side, okay? So you have to include it on the right hand side as part of the energy momentum tensor.
Is this something similar to the self-sourcing of the gravitational waves that we saw earlier? Because this is some contribution to the due to the metric to T mu.
Yeah, so when you have solved for gravitational waves, the source comes from T mu nu, right? But here we are talking about the source in the whole universe, right? So one component of T mu nu just comes from the matter distribution, right? For which we argued that P is 0. Another contribution, if there is cosmological constant term in the Einstein's equation, so that will also give a effective contribution to the energy momentum tensor. And that's what we are trying to calculate now, right? What kind of pressure and P and rho it produces. What is T naught naught here? Yes. T lambda naught naught. T lambda naught naught. Minus C, because G00 is minus 1, right? We have a minus dt square, right? Sitting in front. So this is minus 1, minus C, because G00 is minus 1. What is P? P is even easier to read out. Definition of P, you remember? Where has it gone? Pij is P times Gij, right? That was the definition of P. So what is a P for this case? C, right? Then I have no trick here. Tij equal to P times Gij, right? That's how we are defined. So P should be C. So C, I have not said whether C is positive or negative, right? But by comparing this, we see, so this is rho. We have P equal to minus rho. Yes, indeed. When you have matter plus cosmological constant, then you have to add all of them, right? So let me write P lambda equal to minus rho lambda. if you have a mixture of matter and cosmological constant, right, then you include the contribution of cosmological constant, right, which is minus rho lambda, and matter contribution is 0. Okay. So the rho will get contribution from rho lambda plus rho matter. Okay. P will get contribution only from the cosmological constant, that is minus rho lambda. Matter contribution is 0. Is that clear? This one? Yeah, so what is said here at that we are just looking at this part, right? This part we are interpreting as a contribution of energy momentum tensor, right? And with this we found that rho lambda, yeah, I'm not saying that T mu nu is 0, right? That is the question. If T mu nu had been 0, then this would have been a full rho, right? Otherwise, I can read out the energy density, the contribution to rho from each component and add them up, because T mu nu is just the sum of all these, right? The matter component and cosmological constant component. Okay. So this relation that rho lambda is minus C and P lambda is C, let me write P lambda. This is the contribution due to the cosmological constant, right? So if there is only cosmological constant as no matter, right, then this would have been total rho, this would have been total P, right? Otherwise, the total rho will be the rho lambda plus what you get from matter, and this will be P lambda plus what you get from matter, but you get 0 from the matter, right? Non-relativistic matter. So pressure will get contribution purely from the cosmological constant, but the energy density can get contribution both from matter and cosmological constant. Is that clear? No. It's not related to K. I think, yeah, that K, I mean, in principle, C and K are independent, right? Because you can see that if you can have K equal to 0 in this equation, right? But rho can still get contribution from C. Is this clear? And one of the things you can see that the cosmological constant, this I'll again leave as an exercise, that this equation in principle is supposed to be satisfied by the total rho, right? Total rho and total P, right? Because that's, we have derived this from the Einstein's equation. This is total rho and total P. But if you substitute for rho as rho and P values, right, this equation is automatically satisfied by the cosmological constant. Okay. So the energy momentum tensor due to cosmological constant is conserved by itself. Is that a surprise? No, why not? Yeah, because energy momentum tensor is proportional to G mu nu, right? And G mu nu covariant derivative is 0. So if T mu nu had a term proportional to G mu nu, obviously it should be 0, right? Okay. So if you have a mixture of matter and cosmological constant, right? Cosmological constant is separately conserved, right? And then the matter will satisfy this conservation law, this equation. Okay, so now, so far, we still have the correct number of equations and number of unknowns is still the same, right? Because addition of cosmological constant doesn't really do anything, right? Cosmological constant is just a constant, right? It's not varying as a function of time. C is C, right? It's not a function of time, right? Because then the general coordinate invariance will be broken, right? If you add some function of time times G mu nu in the Einstein's equation. But our universe, okay, also has another component of energy momentum tensor, that is the radiation. Today it's not important. Okay, so today, if you want to do cosmology today, right? Say somewhat far back, we can forget about radiation. Okay, because I will estimate the actual contribution, but it's very small. But suppose it's not very small. In the early universe, we will see that it was not very small. In that case, how will you proceed? Then we need one more relation, right? Because we have, okay, we introduce the rho of radiation and P of radiation, right? Two more variables, right? Two more variables, so you have to supply two more equations somehow, right? Einstein's equation is not helping, right? Einstein's equation has already given the number of equations equal to number of unknowns. So you have, if you have radiation, you have introduced two more variables. So what are those two more equations that you have to use, that we can use possibly? Any guess? Pardon? Maxwell's equations, yes, but what part of Maxwell's equation will you use? Something that you are familiar with? P mu nu of the Maxwell's equation. The radiation you are averaged, I mean, it is isotropic, right? So it's not just simple one electromagnetic wave, it's coming from all directions, right? And you are averaging. So anything about P mu nu that you can say for radiation? Time independent? No, it's not time independent, because as the universe expands, right, the frequency is changing. So it's homogeneous, yes, of course. Right? That has been already gone in. That has already gone in this whole equation. Okay, yes. Yeah, there is some relation. P equal to 1/3 of A. So how will you use it? Yeah, P pressure is equal to 1/3 energy density, but how are you going to use it here? Yes. So yeah, so you know how, for example, the pressure of radiation is related to P mu nu? Yes, that's true. Energy density, right? Tij. Yeah, true, right? But how exactly is pressure related to Tij? Diagonal component. Yeah. The point is I have used the symbol P, right? But I have not said anything about what P is. P in fact is a pressure. And so this P for radiation will be equal to 1/3 of the energy density, right? So that's one equation you already got. Okay. But let me explain why P is a pressure, right? Maybe, and then I'll stop. And then next time, okay, maybe I'll say physically what the other equation is. So P, if you are willing to accept that P is 1/3 rho, right? That P is the pressure, then that's one more equation, right? Equation of state for radiation. But we need one more, right? Because you are missing two equations. The second equation, right, that you are missing, that we have to use some physical insight, okay? Namely that how the radiation exchanges energy with matter. Cosmological constant doesn't do anything. Cosmological constant is just a constant, right? There is an exchange of energy. We cannot change lambda to something else. Okay? But radiation and matter can exchange energy. And we need to have that information to understand how the universe will evolve. The approximation which is good enough for today is that radiation and matter exchange of energy is very small. Okay, that they don't exchange energy, because the amount of interaction that we have, the microwave background that we are seeing today, right, they basically came from a redshift of 1000, okay, far away, without any scattering. Okay, basically the amount of scattering that happens between radiation and matter is so small that you can ignore the exchange of energy between radiation and matter. Okay? That's the physics input. If that is the case, then we can use this equation separately for matter and radiation. See, for cosmological constant, we already argued that this equation is not affected, right? That is automatically satisfied. Rho lambda and P lambda automatically satisfies us. Right? If we say that the exchange of energy between matter and radiation is small, then this equation holds separately for matter density, matter energy density, and matter pressure, right? And radiation energy density and radiation pressure. So this is the input that you are going to use. But this is not the case always, right? In the early universe, matter radiation interaction was strong. In that case, you have to use some other input, right? One in possible input, right, which happens in some part of the early universe, is that if the interaction is very strong, right, then you can imagine that it's in thermal equilibrium. So matter radiation, right, have the same temperature. Okay, and once you say that matter and radiation have the same temperature, that gives another equation. Because temperature, after all, is a function of pressure, and you can express this as a function of pressure and energy density, right? So if the matter pressure and radiation pressure are the same, sorry, matter energy temperature and radiation temperature are the same, then some function of P on rho for matter is equal to some function of P and rho for radiation. So that will supply the basic equation. So this other equation, you have to use this physical insight, right? And for now, we'll just use the insight that in the current universe, the interactions is very small. So we'll impose separate energy momentum conservation on matter and radiation. Is this clear? Okay, so I think I have 5 minutes, so let me just try to argue why this P that we have introduced, okay, is the pressure. Okay, is what we normally call pressure. Yes. No, because we are short of two equations, right? We use P equal to rho by 3, right? That supplies one equation, and then if you impose separate conservation law for matter and radiation, that will supply the second one. So why is P pressure? Okay, and we'll do this in flat space, but you can then use the curved space result by going to local inertial frame. So let's suppose you have a gas of particles, right? The particles could be non-relativistic matter or photons, right? We don't care what it is, right? Let's suppose you have a gas of particles and you are trying to calculate the pressure. Okay, I'll define what pressure is, right? We have information about the T mu nu, and you want to see how from T mu nu we can extract the pressure. Is this problem clear? So you have a gas of particles. Now let's empty out a box, a cube. Okay, so inside is empty. And let's look at some particular surface. This direction, the normal direction, I'll call I direction. Is this clear? Now, Tij. You remember its interpretation? What is Tij? This is the momentum flux, right? So Tij is the flux of the jth momentum in the ith direction. Okay, and in isotropic situation, you have argued that Tij equal to 0. Right? That's also easy to understand, at least from intuitively, right? That why is Tij 0 for I not equal to G? Right? That imagine that you are trying to calculate the flux in the jth direction. And it's isotropic, so the particles are moving in all directions. You are putting a weight factor of momentum Pi in the ith direction, right, which is orthogonal to J. In that case, the number of particles that are moving from left to right is the same as the number of particles moving from right to left on the average. Right? So the average will be 0. But for Tii, right, the difference is that for Tii, you are trying to calculate the average value of Pi. Right? and the surface is orthogonal to pi. So for particles which are carrying positive pi, they are only coming from left to right because they are moving in the positive I direction, right? The particles which are carrying negative pi, they are coming from right to left. So the positive particle pi's are moving from left to right, negative pi's are moving from right to left. Both contribute equally to the flux, right? Because the direction in which the momentum is flowing is opposite, but the actual value of momentum is also opposite. Right? So you carry minus pi momentum along the minus I direction or plus pi momentum along the plus I direction. Right? So Tij gets the same contribution. That's why Tij is non-zero, right? Even when Tii is non-zero even when the situation is isotropic. Is this clear? Okay, so now we have emptied out the inside. And let's ask how much momentum will be coming in and hitting the surface per second, say per unit time. This has area delta in. We want the result in terms of Tii. What do you think the answer is? Tii, remember, is a momentum flux, right? So how much will be the momentum that is coming and hitting this surface per unit time? Tii, and delta A per unit time. Is that right? Everybody agrees? So it's almost right, but not quite. Because if you remember that what we defined as Tii was the energy momentum tensor when nothing was empty, right? The whole thing was full. At a given point, how much is the energy flux? Now you have emptied out the inside, right? So the particles that are coming from this side are not coming anymore, right? The inside is empty. So what should the answer be? By 2, half of this. Now let's suppose that this is elastic, right? Everything that comes hits goes back. Okay, energy has to be conserved, so it goes back with the same momentum or in opposite direction, right? I component gets reversed. So what is the total momentum transfer per unit time on this? 2 times this, right? Because it's coming, hitting and going back, right? So the momentum transfer is 2 times. This is equal to momentum transfer per unit time. That is the force, right? Momentum transfer per unit time is the force on the surface, right? So this is the force on the surface. So what is the pressure? Pressure is force per unit area, right? Pressure is force per area. That's Tii. Okay, so this is the reason why the Tii component that we have introduced, right, which I call P, is actually the pressure of the gas. Okay, if you have a gas of photons, this is the pressure. So from our earlier knowledge, we can use the relation P equal to rho by 3, right? P equal to rho by 3, we can, I don't know if you have seen the derivation of P equal to rho by 3. The thermodynamics course probably, right? P equal to rho by 3, you can get in 2 different ways actually. I mean, you can either think of this as radiation, isotropic radiation, right? We have already written down the energy momentum tensor for the electromagnetic field, right? You have to just assume that it's coming from all directions, you are just average, and then you will find that P is the average value of Tii is actually 1/3 the average value of the energy density. Or you can think of this as a gas of photons, right? Everything moving at speed of light, coming and hitting, right? Just the normal way you calculate the pressure in a thermal gas. Okay? And that will also give the same result, P equal to rho by 3. So we conclude that for radiation, P is equal to rho by 3. And we have this separate energy momentum conservation for matter and radiation. Okay. So now that tells us that we have all the equations now, right? And we can now start evolving and see what we get. Is this clear? Okay, so then tomorrow we'll start analyzing the equations, right? I think you have written down all, we have at least stated all the equations. We'll write down the equations explicitly, and then we'll see how to analyze them. Yeah, so the midterm only, I mean, if I ask original thinking of like in the week of 12, now there is also this in-house, right? But that week itself we'll have to do is sometime. Because the idea was that you will submit the homework problem for assignment B. And the midterm will basically based on up to that point. Assignment B, so that means that anything so I'll maybe send out a message today. It will be sometime in that.